We have talked about many kinds of elastic constants for a linear elastic isotropic material. We've talked about the Lami's constants, which are lambda and mu, which are Lami's constants. Uh, but then mu is also called the shear modulus. We have talked about the Young's modulus. We've talked about the Poisson's ratio. We have talked about the bulk modulus. The point is, why do we need so many? The reason is kind of historical. The reason is that the way we measure these constants allow us to determine certain of these constants more easily than others. Okay. For example, if you take the linear elastic isotropic relationship and you take the shear stresses, say let's say sigma 1 2, we have sigma 1 2 equal to 2 mu times epsilon 1 2. So we start with the stress strain relation. Sigma ij is equal to lambda delta ij epsilon mm plus 2 mu epsilon ij. So if we put sigma 1 2, then this goes to 0 and you are left with epsilon 1 2 times 2 mu. So this is your stress strain relation. And if you can now do a test where you apply only sigma 1 2 to the specimen, where you can be pretty sure that you have been able to make a specimen for testing so that only sigma 1 2 is applied to that material, to that specimen, then you can directly measure sigma 1 2, measure epsilon 1 2 that you get, and the ratio of the two would give you shear modulus directly. So this is known as a uniaxial shear test, uniaxial shear. Similarly, from here you can immediately see, and we have done this before, sigma kk is equal to epsilon lambda 3 lambda epsilon mm plus 2 mu epsilon kk. Kk and mm are the same, so this is 3 lambda plus 2 mu epsilon kk, and this quantity we call it as 3 times the bulk modulus. So again, if you can do a test where you are sure that you are applying hydrostatic stress only, this is called hydrostatic stress. This is the trace of the stress tensor, trace of sigma. It's called the hydrostatic stress. Actually, it's called 3 times the hydrostatic stress. 1/3 of this is called the hydrostatic stress. So this is, you are sure that you are applying purely hydrostatic stress. For example, if you take it under the sea, at a very great depth, if you take a block of steel under the sea, you are pretty sure that you are applying only a hydrostatic stress. Then for an isotropic material, you will get only a hydrostatic strain, and then the ratio between them, if you can measure sigma kk and epsilon kk in such a situation where you have applied only a hydrostatic stress and nothing else, then the ratio between this hydrostatic stress and the hydrostatic strain would straight away give you the bulk modulus. So if you can do a uniaxial shear stress shear test, you will be able to get the mu. If you are able to do a hydrostatic pressure test, then you will be able to get the k directly. And then from these, going back to the table, you will be able to get the lambda and mu or whatever constants you want. Getting the Young's modulus is also easy, and it's a very standard exercise actually. And this is how it goes. So let us consider a situation where I am pretty sure that I have a sample. I have made some sample where only sigma 1 1 is not equal to 0, and all other stresses sigma ij are equal to 0. So all other sigma ij are equal to 0. Suppose I am guaranteed that I have generated a sample. I have generated a sample geometry which follows this. In that case, only 3, so all the shear stresses are 0. So the shear stress, shear strain equations don't even come into the picture. So I have all 3 equations involving the normal stresses. So sigma 1 1 is a lambda epsilon mm plus 2 mu epsilon 1 1, and then 0 is equal to lambda epsilon mm plus 2 mu epsilon 2 2, and 0 is equal to lambda epsilon mm plus 2 mu epsilon 3 3. What you see from these two equations immediately is epsilon 2 2 is equal to epsilon 3 3, and both are equal to minus lambda by 2 mu epsilon m m. But now epsilon mm is epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3, but 2 2 and 3 3 are the same, so let's say write epsilon 2 2. So uh, this is now equal to uh, so here epsilon 2 2, this is now epsilon 1 1 plus or minus uh, lambda by 2 mu epsilon m m. So epsilon 2 2 2 times. So take it to the other side. Epsilon 1 1 will now be lambda plus mu by mu epsilon mm. Okay, plug this into here, so you will get this as lambda times lambda plus mu by mu epsilon, oh sorry, the other way around. So you will have lambda times mu by lambda plus mu epsilon 1 1 plus 2 mu epsilon 1 1, which means now sigma 1 1 will be expressed completely in terms of epsilon 1 1. So if you can do a test where you are pretty sure that you are only applying sigma 1 1 and sigma 2 2, sigma 3 3, all other components are equal to 0, if you have a specimen of that sort, then you will be able to measure the epsilon. You can measure the stresses sigma 1 1 and the strains in the same direction epsilon 1 1, and the ratio between them will give you what is known as the, so this constant that you get from here will lead you to the Young's modulus, and this is what we generally measure in uniaxial testing machines, which are pretty standard machines that are available in almost any lab. So so once you get E from this, again you can go back to your table and get any other constants depending on what you need. Okay, so let me stop here again.